Okay, so we'll see today the k-means algorithm. K-means is one of the unsupervised learning algorithms. So till now we have done supervised learning. So unsupervised learning in the sense, as we said, that there is no specific right or wrong. We can't calculate the so-called cost and then minimize the cost function with respect to the actual target variables. There are no target variables which are labeled, which says that suppose cancer is yes, or there is cancer, or there is no cancer, or some value of the share price, say it's 1000 or 1100 or 1200. There is nothing like that. There is no specific level for any unsupervised learning algorithms, or for that unsupervised data. Example of unsupervised learning algorithms are like, say, um, we are doing a social media analysis. So social media data might be, say, a Twitter feed or a WhatsApp posts or Facebook posts or anything. So let's say we are analyzing the Twitter feeds. So Twitter feeds is just the tweets or the posts which have been made by, say, groups of individuals in Twitter. So there is nothing right or there is nothing wrong in that data. It's just data as such. When we do unsupervised learning, what we need to do is we need to analyze the data and try to figure out that what the individual or the group of individuals might be saying. Based on that, we might be forming some interest groups, and based on that, we might be segregating the individuals. We might be dividing the individuals into groups or clusters. So there is no hard and fast rule, or there is no in the data itself there is no label which says that this has to be told by this word, has to be there in the tweet. There is nothing like that. We will do hands-on going forward. At that time it will become more clear. There can be other examples. Say these online news are grouped into different categories. That is all done by clustering. So unsupervised learnings are broadly classified into like two types. One is clustering, another is these recommendation rules. So recommendation rules are usually whatever you see in the e-commerce sites or in the big stores like Big Bazaar or More or anything, or the Walmarts. So you see that people who have bought this have also bought, or people who have liked this have also looked into these categories. So all, or for Netflix movies, say you watch any movie, and based on that movie or based on that interest, Netflix keeps on recommending you different movies. So all those are part of the recommendation. So recommendation type algos. Recommendation type algos are, once again, can be like broadly two types. One is the recommendation engine, another is the association rules or the a priori algorithm. We'll discuss those afterwards. Today we'll discuss clustering, because clustering is more difficult than recommendation rules. So both clustering and recommendation rules, they have widespread, uh, they are used in the industry heavily. They have widespread use in the industry. Supervised learning, whatever algorithms we did, not all algorithms are heavily used in the industry. Whatever algorithms we did of late, like decision trees, and we started with neural networks, those are heavily used. Even when we will be doing support vector machines, those are heavily used. But algorithms like basic linear regression or basic logistic regression, they might not be so popular in the actual industry. Whereas in contrast, whatever we'll be doing for unsupervised learning, they are heavily used in the industry, actually used. Say for example, recommendation rules everywhere. clustering everywhere. Everyone does some social media analysis or something, or say everyone tries to categorize the news, or someone wants to do this exit poll. They want to form clusters based on the voters, based on their interest. So clustering analysis heavily used, recommendation rules heavily used. Okay, so let's look at clustering. Okay, so in clustering, once again, there are one type of clustering. So I will not say that there are really two types. Rather, let's discuss the different types. So in one type of clustering, so whatever you have seen on the screen, K means clustering. We will discuss this in details. So in this type of clustering and in other algos, we initially define how many clusters or how many groups we want. Okay, so we have the data. Before starting the algorithm, or when we are starting the algorithm, we know that how many clusters we want. How many clusters in the sense that we want to group the data into how many clusters, or we want to partition the data into how many groups. So that number we already know. We already know in the sense we do not know by some magic or something. It's just some intuition, or we have already decided that I want these many groups. That's it. So this is one type. So here K means belongs to that type. Here K stands for the number of groups or the number of clusters. So if I want my data to be divided into 3 groups, I will tell it as a 3 means clustering algorithm. So K stands for the number of clusters or the number of groups which are decided before starting the algorithm. Okay. Then there is another type of clustering which is called hierarchical clustering, where the number of groups is not pre-decided. We start with the data and the algorithm proceeds, and the algorithm finds out that, or ultimately when the algorithm stops, it divisions the data into certain number of groups. That might be 3, that might be 10, that might be anything. So number of groups is not chosen a priori, or number of groups is not chosen before the algorithm starts. Out of these two, the first type, where the number of groups is pre-selected, that is much more common. We will discuss that in detail first, and then we will also discuss the hierarchical clustering, where the number of groups are not chosen before the algorithm starts. Okay. Let's now discuss k-means algorithm. So as we have discussed that clustering is an unsupervised machine learning, and so okay, and one more thing is which is very important. So earlier we had done one algorithm called KNN. You would all have remembered. So KNN we did, that was a supervised learning algorithm. So when we say supervised learning algorithm, that means there were specific levels. So for example, we were doing this project where we were trying to identify possible breast cancer patients. So we were one of the algorithms which we tried was KNN. So here the data itself had specific levels that these patients are suitable candidates for breast cancer and these patients are not. So it's already labeled. So k-means and knn, although it in both the algorithms this word k or this letter k is there, but they are completely different algorithms. But they have some common philosophy which we will discuss just now. So knn is a supervised learning algorithm. K-means is a completely different algorithm. It's an unsupervised learning. Okay, so don't mix these two. Okay, so the thing which is common between k-means and knn is the distance. So both of these algorithms work based on the distance between the point, or the metric for the performance of the algorithm is the distance between the point. That's how the algorithm, both these algorithms are calculated. So that's why both have these k-means. So in knn, what was k here? So in knn, in the supervised learning knn, k stands for how many points. So if say for knn, if say k is 4, that means the algorithm will be calculating the distance of the 4 data points. So it will basically calculate the distance and it will select the 4 nearest data points with respect to a data point, and based on the groups. So let's say I'm doing a breast cancer analysis. I have chosen k equals to 4. I have a new data point. I calculate the distance of all the data points and then I select the 4 nearest data points which have the shortest distance with respect to the new data point. Okay, so with respect to distance, I have chosen my 4 nearest data points. My k is 4. Out of these 4 data points, if 3 data points belong to the group where the breast cancer is no, and 1 data point belongs to the group where the breast cancer is yes, then I will say that my new data points also belongs to the group where breast cancer is no, because the majority of the nearest data points out of 4, 3 points belong to that group where breast cancer is no. So the new data point will also likely belong to the same group. That was knn. K-means, in k-means, k stands for the number of clusters or the number of groups that we want before starting the algorithm. So before starting the algorithm, I have the data, and if I say that I want to divide the data into 5 clusters or 5 groups, then my k will be 5 here. Okay, so my k will be 5 here. So I will start with k equals to 5. Okay, so look at the 6th point. So k stands for the number of clusters that we want to split the data into. So if I say my k is 3, that means before starting the algorithm I have decided that I will split the data into 3 groups. Okay, it is prefetched before running the algorithm, and when doing the hands-on we'll see that we can give this k. So the user has the option to give the value of k. K is just a variable. Okay, uh, so let's see an animation to understand how k-means work. Okay, so let's say that I have let's say I have 100 data points, whatever you see the white dots. So let's say these are my 100 data points. Okay, and I have chosen my number of cluster, which is k, as 5. Okay, I have given the value of k as 5. So the first step which is being done is, as soon as the k is supplied to the algorithm, 5 data points are randomly selected. So you can see here that this red cross is a data point. So so if I say five clusters, so out of the 100 data points, or out of the total number of data points in, 5 data points are selected as the center of the 5 clusters. If I say k is 5, that means I want 5 groups or 5 clusters, right? So when the algorithm starts, the initial step is to select those 5 or the k data points randomly as centers of the clusters. These points might not ultimately end up as the centers of my 5 clusters, but randomly 5 points are chosen. If k equals to 5, if k equals to 7, then 7 points will be chosen randomly initially. So here I have given k equals to 5. That means 5 data points are randomly chosen to be the center, or to be the centroid. So it's basically the centroid. Centroid is nothing but the center of the clusters. So 5 data points are chosen randomly as the centers of those 5 clusters. Okay, so whatever you see here, this red cross, green cross, and this blue cross and purple cross, these are the 5 cluster centers initially randomly chosen. So red, light green, deep green, blue, and purple. Okay, whatever you can see here, this cross, this 1 2 3 4 5. Okay, now the next step is the distance is calculated between each data point and the centroid. So basically the distance is calculated between all the data points and all these centroid, all these centers, and the rest of the data points are separated into clusters, are separated into 5 groups here based on the shortest distance. So let's say, for example, if we take say this point, this white dot, so distance is calculated between this white dot and this first cluster center, blue cluster center, between this white dot and this purple cluster center, between this white dot and this green, between this white dot and that green, and between this same white dot and the red. So out of all these 5 distances, that as you can see here, the distance between this white data point and this blue cluster center will be the minimum. So hence this white data point will belong to this cluster, where this blue cluster center, where the cluster center is this blue point. Okay, so based on the distance, based on the Euclidean distance, the distances are calculated between all the data points and the cluster centers, and based on the shortest distance, all the data points are divided into groups, into these 5 groups. So let's visualize this step. So see, all the nearest data points go to the respective cluster centers. Now let's take any group. Let's take this purple group. Now we had chosen the cluster center randomly, right? Now in this cluster, in this purple cluster, whatever is being formed, in that definitely this our initial choice of this cluster center is not the perfect choice of the cluster center. So what I mean to say is that this is no more the cluster center. So maybe some point here or some point here will be the actual cluster center, right? This was our initial guess, and our initial guess will be wrong. So the next step what is being done is, for each group the proper cluster center is recalculated. The proper cluster center is calculated, not recalculated. The first time it was initially chosen, this time it is actually calculated. So basically the mean of all the, I mean whichever point is the mean of all these data points, that point is chosen as the cluster center. So let's visualize that step. So now you will see that the groups will remain same, the cluster center will change. So see, the groups have remained same, the cluster center has changed. Okay, so now what is being done is excuse me, what is being done is, so now initially when the clustering was done, so initially when the distance between all the data points and the cluster center was calculated, at that time our initial cluster centers were something different. Now the cluster centers are different. So that means now if we redo that step where we calculated the distance between all the data points and the cluster centers, and with the new cluster centers, then some data points will move from one cluster to another, because initially we had done it with a different set of cluster centers. Now our cluster center has changed. So if we repeat that step, what we will see is some data point will move from one cluster to another. So for example, let's take this data point. Initially our purple cluster was somewhat like this here. So hence this data point, this purple data point was close to the earlier cluster center, but now the cluster center has shifted and this green cluster center has also shifted. So maybe, and this blue has also shifted. So maybe now this data point which initially belonged to this purple cluster might move to one of the green or the blue cluster based on the new cluster centers, right? So let's visualize that step. See, this point moves to the green cluster. So like that some points move from one cluster to another. So now it's all the clusters are new because some data points move from one cluster to another cluster. As the cluster changed, the cluster center should also change. The previous cluster, that means the second cluster, whatever was calculated, that now once again is not correct because the clusters have changed. If the cluster changes, that means cluster center also has to change. So now once again the cluster center is recalculated. See, once again if the cluster center changes, some points might move from one cluster to another cluster. Let's redo that step. Now once again the cluster center is recalculated. Once again let's see if some point moves from one cluster to another. It moved. Cluster center once again recalculated. Once again some points moved. Recalculated cluster center. Some points moved. Recalculated cluster center. No points are moved. So after certain iterations we will see that the clusters are now perfect. That is, in whatever way it is distributed, they are actually near to the proper cluster. So the data is grouped into proper cluster. There is no more movement which is required. So if we had chosen 5 clusters, so these are our 5 cluster centers and these are our 5 clusters. The data is grouped into 5 clusters. Okay, so this is the k-means algorithm. So in k-means, once again, one of the disadvantage of k-means is how do we select k, right? So that is one of the contention points, that what should be an ideal value of k. So we have one popular method which is strangely named or strangely called as the elbow method. So we'll see that, but in most of the actual real life cases, K comes from the domain knowledge or your intuition that I want the data to be divided into these 7 clusters or these 3 clusters or these 9 clusters, whatever, 10 clusters. So that's how K is decided. We can use this elbow method. Now we'll discuss this just now, but it's up to you if you want to use it or not. You might want to use it, you might not want to use it. So okay, if you do not have a priori knowledge, and if you do not have domain knowledge or the intuition, if you do not want to select the number of clusters before, but still if you want to do k-means, you will have to supply the k. K-means cannot work without the initial supply of k. So what you can do is, you can choose different values of k. So if you see the graph here, the x-axis says that number of clusters, okay, and you can use a metric that the sum of squares within a group. That means, so if I choose 2 clusters, then the data is divided into 2 groups, and for each group the sum of squares is calculated. So what is sum of squares? Sum of square is the Euclidean distance between each data point in a group and its cluster center. So that is calculated and summed up. So that so naturally for less number of clusters, the value will be more because we'll have less number of clusters, right? So the distance will be more. So that we will see that as we increase the number of clusters, the value of the sum of squares will decrease rapidly. So see, from 2 to 4 it's decreasing, from 4 to 6 it's still, I mean 4, 2, 3, so we tried with 3, 4, 5, so it rapidly decreases, and then say at 6, after 6 it decreases, but the decrease is not, the rate of decrease is not so rapid. So so it basically resembles the shape of a human elbow. If you fold your hand, it looks like this. So this is kind of a your hand, human hand, and at when the number of clusters is 6, so that is basically your elbow. So if this is our hand, this is our this part is our arm, and this part is above the elbow, then this point at 6, this so I mean this kind of represents the elbow, so that's why this method is strangely called the elbow method. So we will say that maybe the best choice for k is 6. So the point at after which the rate of decrease of the sum of squares decreases, or the sum of square does not decrease so rapidly, that point is chosen as the optimal number of clusters. So you can either use this, or you can go with your own intuition or your domain knowledge that I want this many clusters. Okay. Okay, now let's see if this is clear, then let's do hands-on. Okay, before the hands-on, so we discussed this distances. So in while doing the KNN, we were just touching upon the different distances. So here also there are different distances. So yeah, both for k-means and KNN, by default the Euclidean distance is used, but it is worthwhile to know other distances like Manhattan distances and Minkowski distance. So I'll just write what is the Manhattan distance and the Minkowski distance. So Manhattan distance is Okay, so what is Euclidean distance? So let's say this is the Euclidean distance. So Euclidean distance is basically h2 minus h1. So what we are doing, say if h1 is our cluster center, if h1 is our cluster center CC, then we take all the points, right? h2, h3, h4, like that. And so h2 minus h1, so we square it, and then so let's say our point is h1 y1. Okay, say so then y2 minus, let's say we are doing it on just two axes, so y2, so y1 is once again our cluster center. So basically our cluster center is, our CC is, so we have chosen, let's say, one of the pointers h1 y1. So this is one of the CC, and let's say some other CC is h7 y7. Let's say we are doing it with two clusters, and these are our two cluster centers. Okay, so I'm doing it only for the first cluster center. So when we were doing, if we are doing Euclidean distance, then we do a sum of the squares, and then we ultimately square root, right? So this is our Euclidean distance. So this now Manhattan, so this is Manhattan. So Manhattan distance is Manhattan distance says that we do not square it, instead we just take the mod. So we just do the h2 minus h1 and we take the mod, and we sum it over other whatever y1 whatever is there, y or z or whatever is there. So we just sum it and take the mod, and we do not square it also. Okay, so this is Manhattan distance, this is Euclidean distance. Now the thing is, so there is one more distance which is actually the true formula, which is called the Minkowski distance. So Euclidean distance and Manhattan distance are both variations of the Minkowski distance. Okay, so let's see the Minkowski distance. So Minkowski distance, Minkowski okay, let's say this is the Minkowski distance, something, some spelling is like this. Okay, let's say this is the Minkowski distance. So the Minkowski distance says that, so whatever, say h2 minus h1 we did, right? And then we did some, for Euclidean distance we squared it, for Manhattan distance we didn't square it, right? So let's say this is C, whatever this power, this is C, and then we summed it, then we did a sum, and actually say we further used a power of 1 by C. So for Euclidean C is 2. C is 2. For Manhattan, C is 1. So when C is 1, so if C is 1, that means we were just taking the difference and then we were obviously doing a mod, because so that the sign doesn't come, and then 1 by C is basically 1 by 1, so it's just 1, so anything to the power of 1 is just that number. So that was Manhattan. For Euclidean we were squaring it and then we were doing a square root, right? So square root is what? Square root is multiplying by the power of half. So this is the actual formula. This Minkowski. This Euclidean and Manhattan are the variations of the Minkowski when C is 2 and C is 1 respectively. So in the Minkowski distance, if we put C equals to 2, then it becomes an Euclidean distance. In Minkowski distance, if we put C equals to 1, then it will become Manhattan distance. Okay, so that's it. So now let's do some hands-on. Okay, so let's look at some unsupervised data. So I have taken some unsupervised data. So let's say this is the social media data of certain teenagers, okay, and say some sports company, let's say Nike. Nike wants to launch some product, let's say some whatever, let's say some shoe. Nike wants to launch some shoe, some sports shoe, and it wants to target the teenagers. So it basically Nike wants to launch some sports shoe for teenagers, and hence it wants to focus on teenagers. So when machine learning was not there, what Nike would have done? Nike would have given some newspaper ad or some online ads. Now the problem with that is Nike doesn't know that who is reading those ads. So the teenagers might be reading those ads or might not be reading. Okay, if Nike gives an ad in the newspaper, there is a high chance that teenagers might not be reading that newspaper. So hence there is no question of the ad even reaching its targeted audience. The target audience for Nike for this product is teenagers. It wants to target only the teenagers. So with machine learning it's much more logical, and that's what machine learning, this is how machine learning has helped. So what we can do is, what Nike can do is, say so Nike has got the social media data from one of the channels. Let's say this is whatever, let's say this is Twitter. So Nike has got the social media data of teenagers, and then Nike has some keywords like say basketball, football, say cute, hot, tennis, cheerleading, swimming, and then say religion, church, clothes, shopping, all this. So Nike has these keywords, and it wants to target only those teenagers which it thinks are interested in sports. So basically Nike wants to cluster the data, the social media data, into groups, and it will then target only those individuals which are interested in sports. Okay, that is the whole point. So I've read this data. So here you see the first 4 columns: graduation year, gender, age, and friends. So these first 4 columns are coming from the profile itself. So the social media will have some profile information, right? So this is coming from the profile itself, and then the remaining columns are the actual social media data. So the numbers indicate that how many times this word has been used in the tweet or in that post. Okay, so each row is the data for each individual. So now we have done some data cleaning beforehand, so which we already discussed. So here what happened is, if we do a say this gender. So see here that there are so many NAs, so many not applicables. Similarly, if we do for age, so initially the data was having many NAs. So what we did is we cleaned those NAs intelligently, as we discussed in the class. That what we did is we took the graduation year and we took the average age of the graduation year. So with respect to graduation year, we can find the age, right? If someone graduates in say 2006, that means age might be like this. If someone graduates in 2010, age might be something else. So in all those missing ages, so what we have done is we have checked that what is the average year for each graduation year, and then instead of blindly filling it with the mean of the age or some other value, we have done it intelligently. We have checked what is the graduation year for that individual and what is the average age for that graduation year, and we have filled it with that age. Okay, so that part we have already done, and we have also normalized the data. Okay, so once we have normalized the data, then let's run the k-means. Yeah. So after our data is normalized, the new variable is this interest underscore z. So this is our new data. And we have taken only from the fifth column. So first to four column are not required because these were the profile information. So we are interested in only the tweets or the social media data, which starts from the fifth column, from the basketball till the whatever this 35 or 36 column. So we have taken that and then normalized it with the inbuilt method called scale, and then here we are trying to run the k-means algorithm. So just see the syntax. So this is the teen clusters will be the model and k-means is the algo. We supply the data. Our data is interest underscore z, and then 5. So what is 5? Yeah, so 5 is the cluster or the number of clusters that we want, number of groups that we want. So initially the 5 data points will be randomly selected, then the distance between all the data points with respect to these 5 data points will be calculated, then the center will be recalculated for those 5 clusters. So since the cluster has changed, some data points might move from one cluster to another. That step will happen. Then once again the cluster center will be recalculated, and so on. So the algo will stop when there is no further movement of any point from one cluster to another cluster. Okay, so let's run this. Okay, so we have got it. So if we see that so this is our model. So now let's check some attributes. Okay, so one is size. So see size, if we do a size, it comes up with this 5 numbers. So these are the 5 clusters. So basically I have supplied 5, right? So it has come up with 5 clusters, and so the first cluster has this 22,000 data points, second cluster has 694, third has 1059, fourth has 609, and the last one has 5581. So these are the sizes of the clusters. So now let's look at some other attributes. So now let's look at the centers. Okay, yeah, so this is what is important. So you look here. So we have all the keywords, this basketball, football, soccer, whatever keywords we had used. So for each keyword, the 5 clusters values are given. So now let's go to the algo. Let's go to the PPT once. Yeah. So now look that. So this is the same thing. This is what you are seeing in the art studio. So here we have the keywords and we have the data for each cluster. So see, for each keyword we have 1 to 5. Now we will have to understand that which cluster is more inclined to sports, right? So just look at the values. So these are the mean values. So see that for all the keywords which are related to sports, say basketball, football, volleyball, swimming, baseball, tennis, the third group or the third cluster has its centroid values above the mean level. So that means that this third cluster must be interested in sports. See, the value of this third cluster's mean is high. So that means that this third cluster is interested in this sports. Okay. Now, so we can conclude that this third cluster, we can target this third cluster for our sports. Okay. So that is how it is done. So we can do a cluster. So we can with our model we can do centers, and then we can see based on our interest, if you are interested in finding out the group which which we want to target for sports, then we look at the sports keywords and we see that which cluster's central value is higher. Now we have identified that which cluster we have to target. Now we have to find out that which points belong to that cluster, right? Which are the individuals that belong to the cluster. That we can do by this thing, by cluster. So if we now write cluster, so what will happen is, see, the first row, these are the keywords. So we can see that it belongs to, for each of the keywords, what is the where it belongs. So like this we can actually select the individuals, that which individuals belong to which cluster for our groups. Okay, so this is how it is done. Just before we close, so we discussed this hierarchical clustering. So hierarchical clustering, what we said is that the number of clusters is not chosen beforehand. So instead, in hierarchical clustering can be once again into two broad types. So one is bottom up, another is top down. Okay, so in top down, so top down is also called divisive. So the hierarchical clustering which does a top down algo, that is called a divisive hierarchical clustering, and the bottom up approach is called a agglomerative hierarchical clustering. Okay, so what is that? So let's just try to visualize it. So let's do bottom up, let's do agglomerative. Okay, so let's say we have these data points, we have this all the data points lying here and there. let's say these are the data points. Let's say these are my data points. Okay, so in agglomerative or in bottom up, what is considered. So remember, this is hierarchical clustering. We do not supply the initial number of clusters. So we do not supply how many clusters we want. The algorithm decides on its own. In hierarchical clustering, the k is not supplied or the number of clusters is not supplied. The algorithm decides on its own. The problem with hierarchical clustering is these are very slow and these do not give good results. So that's why these are not so common. Okay, so in bottom up or in agglomerative, what is the concept is, initially we consider all the data points. So if I have, let's say, some 1000 data points, all 1000 data points as individual clusters. So each data point is a cluster. If I am having 1000 data points, I have 1000 clusters. Okay, so here whatever data points I have, all of these are individual clusters. So individual cluster means all of these are individual cluster centers. So next step what is being done is, the distance is calculated between each data point with respect to each other. So this is a huge process, right? Because the distance of all the data points with respect to each data point needs to be calculated. This is a huge step, and based on whatever metric we use, say it should be less than some distance or whatever metric is being used by the algo, the initial clusters are formed. So let's say this forms one cluster, this forms one cluster, this forms one cluster, and so on and so forth. Okay, then what happens? Then the cluster center is selected for all these clusters, and then the same process is repeated. So then we see that whether the clusters can be combined. So here maybe whatever is our metric, so once the cluster center is shifted, maybe these data points have now belong to one cluster. So similarly, this is our new cluster, and this is our new cluster, and finally this is our new cluster. So from 5 we came to 4, and let's say we further do it, and ultimately let's say we end up with 3 clusters, something like this, this and this. So what happens is, we go bottom up, right? Bottom is all the points are individual clusters. Next step, what we do is we try to we try to see based on our metric that how many points we try to reduce the number of clusters. So for top down or for the divisive, the exact reverse thing is being done, that we start with just one cluster and we break it down into how many cluster it breaks. So that is called divisive. Okay, so let's stop it. I'll stop the recording.